If you were to take the pulse of a lake to check its most vital sign, you wouldn't use a stethoscope. You'd measure its breath. You'd measure dissolved oxygen. Dissolved oxygen, or DO, is one of the single most important indicators of a lake's health. It governs nearly every process in the ecosystem, from whether fish can survive in the depths to whether the lake's own sediments will poison it from within. Most of the life we see and don't see in a lake requires adequate oxygen to survive. Fish, the tiny zooplankton they feed on, and the crucial benthic organisms living in the mud at the bottom all depend on healthy oxygen levels throughout the entire water column. So, how do scientists take this vital measurement? They create something called a dissolved oxygen profile. Imagine a scientist in a boat lowering a probe on a long cable into the water. This probe, often an optical or electrochemical sensor, takes a reading of the oxygen concentration at different depths, foot by foot, meter by meter, all the way from the shimmering surface to the dark lake bed at the very bottom. This series of measurements creates a vertical snapshot of the lake's breadth. The results are then plotted on a simple graph that tells a complex story. Picture the horizontal axis showing the depth, starting at 0 at the surface and increasing as you move right. The vertical axis shows the oxygen concentration measured in milligrams per liter. This graph, the DO profile, reveals exactly how the lake's blood life is distributed from top to bottom. Learning to read it is like learning to read a lake's medical chart. Let's break down what we see, starting at the top. The first section is the surface layer, what limnologists call the epilimnion. This layer is usually teeming with oxygen. Sunlight penetrates here, driving photosynthesis and algae, which releases oxygen as a byproduct. At the same time, wind churns the surface, mixing oxygen from the atmosphere directly into the water. So on our graph, the line starts high on the oxygen axis, showing healthy, well-aerated water. As we go deeper, we hit the middle layer, the metalimnion, which contains the thermocline. This is a zone of rapid temperature change, and it acts like a powerful barrier. Think of it like a lid on the bottom half of the lake. It dramatically limits mixing between the warm surface waters and the cold, deep waters. Because of this barrier, oxygen from the surface has a hard time reaching any further down. On our graph, this is where the oxygen line often begins its steep descent. Below this barrier lies the deep layer, the hypolimnion. This part of the lake is completely isolated from the atmosphere during the summer. It's dark, cold, and cut off. Here, oxygen can only be consumed. It cannot be replenished. Bacteria on the lake bed decompose dead algae and other organic matter that rains down from above, and this process uses up oxygen. So, throughout the summer, the oxygen level in the hypolimnion only goes in one direction, down. The DO profile shows this as a sharp decline, with the line plunging towards the bottom of the graph. To understand the severity of this decline, scientists use specific thresholds. Imagine drawing horizontal lines across our graph. A line at 6 milligrams per liter represents water healthy for most fish. Between 4 and 6, the habitat quality is good enough, but once the oxygen drops below 3 milligrams per liter, fish really begin to struggle. At 2.5, we enter a state called hypoxia, critically low oxygen. Fish and other mobile creatures will flee these zones if they can, effectively losing a huge portion of their habitat. And if the oxygen level hits 0, that's anoxia. Nothing that needs oxygen can survive here. For the benthic organisms, the worms and insects living in the sediment, prolonged hypoxia is a death sentence. This brings us to the most critical part of the story, why that deep water oxygen level is the key to everything. The deep layer, the hypolimnion, controls the lake's long-term stability. When its oxygen disappears, the lake begins to lose its resilience. A dangerous chemical switch gets flipped in the sediment. Under healthy, oxygenated conditions, lake sediments act like a vault, locking away nutrients, like phosphorus and nitrogen. But when oxygen vanishes, the chemistry changes. The vault door swings open.
Phosphorus and nitrogen stored for years in the sediments are suddenly released back into the water. This process is called internal loading. This newly released phosphorus doesn't just stay in the deep, it becomes a super fertilizer, fueling massive algae growth at the surface. This accelerates the entire process of eutrophication, where the lake becomes choked with excess life, leading to a vicious cycle. More algae means more dead organic matter raining down, which means more decomposition, which consumes even more oxygen, which in turn releases even more phosphorus from the sediment. The lake begins to feed its own decline. At the same time, the loss of benthic organisms is devastating. These creatures are the cleanup crew of the lake bed, processing organic matter and supporting the food web. When they die off, sediment builds up faster, and even more nutrients are released. This entire drama plays out across the seasons. In summer, the sun creates a warm surface layer and strong stratification, preventing any mixing. This is when the deep layer is most vulnerable, often becoming hypoxic or even anoxic. But then autumn arrives. The air cools, and the surface water cools with it. As it cools, it becomes denser and begins to sink. Eventually, the entire lake reaches a uniform temperature, and the winds can mix it from top to bottom. This event, called autumn turnover, is the lake's great exhale and inhale. It replenishes the deep water with life-giving oxygen, resetting the system. In winter, ice can form, reducing mixing and light. Oxygen levels slowly decrease again, but because biological activity is much lower in the cold, the decline is usually not as severe as in summer. Then comes spring. The ice melts, the water warms towards 4 degrees Celsius, its point of maximum density, and the lake mixes completely once more. This spring turnover is the lake's final deep breath before the summer stratification begins all over again. By taking DO profiles regularly, year after year, scientists can read the lake's long-term health history. They can ask critical questions. Is the deep layer losing its oxygen earlier each summer? Is the hypoxic dead zone getting larger? Are fish losing more and more of their habitat? Is the risk of internal loading increasing? Long-term monitoring can reveal if a lake is slowly sliding towards an irreversible decline or if restoration efforts are actually helping it recover. The key signals they look for in a DO profile are the strength of the stratification, the depth of that thermocline barrier, the rate of oxygen depletion in the deep hypolimnion, and the timing of the seasonal mixing. In essence, a dissolved oxygen profile allows scientists to measure oxygen at all depths, understand the lake's mixing patterns, evaluate its biological health, and predict the risk of nutrient release from the sediment. Ultimately, the story of a lake's health is written in its deep water. The oxygen level in the hypolimnion is the single most important indicator of whether that lake is resilient and stable or whether it is at risk of entering a downward spiral of decline. It is a simple line on a graph, but it tells us everything we need to know about the breath, the life, and the future of the water below.
Measuring oxygen tells us the real-time mood of a lake. But to see its long-term memory, we have to look even deeper. Join us in Lesson 7, Muck Never Lies, where we use sonar and Secchi discs to read the history written in the muck and sediment in the lake bed. To go to the next lesson, use the link below. And don't forget to subscribe, like, and share.